All right, welcome back, Patriots. Let's go ahead and get started on our next unit, which is going to involve everything from simplifying radicals to Pythagorean theorem to the dreaded word trigonometry, which is actually a whole lot easier than it sounds, but we'll get to that on a later day. Today, we're going to be focusing in on square roots and radicals. And the reason that this is a big deal is because tomorrow, when we get to Pythagorean theorem and also the converse of the Pythagorean theorem, knowing how to properly handle roots is going to be a important thing for you to have down. So let's go ahead and jump straight into it. The first thing is this word radical. I'm not going to get into the reasons why on this video or why it's called a radical. I might do that in class one day because it's actually a pretty fun story. But for now, what you need to know is that the radical sign is this thing that we've traditionally called the square root sign. Now, there's actually a whole bunch of different versions of the radical sign, but the most common one is the square root. So the first thing is you need to know the different parts of it, okay? The number on the inside, okay? This number, let's just use a 9 there. This one is called the radicand, okay? The radicand. The radicand is the thing underneath the radical sign. This right here is the radical sign. And now, one of the things that you probably haven't seen before is that there's also a number up here. This number is called the index. So there would be something like this. Now, the way you would properly read this is the third root of 9. Okay, so if I had this, and I had 5 and 27, this would be the fifth root of 27. Now, I say third root here. The number 3 there can also use the exact same naming system as like when you have this. You can say x to the third. You can also say x cubed. So if I said the cubed root of 9, that just indicates that the index is 3. Now, you're used to seeing things like, well, the whole thing is called a radical. Now, you're used to seeing things written just like this. You're used to saying that the square root of 4 is equal to 2. When there's nothing there, okay, when this is missing, so if the index is not written, it is always understood to be a 2. Now, this is a slightly different thing than you're used to because typically whenever something is not written there, it's usually understood to be a 1. Like, for example, if I had x squared plus 3x plus 4, you know that there's a coefficient there, but it's the hidden 1. Okay. Also, on our exponents here, we have an exponent of 2 there, and here there's this understood exponent of 1. In this case, if there's nothing written there, it's an understood index of 2. And I'm putting those in dotted lines to show that they're there, but they're not really there. Okay. You just don't see them. Now, this entire lesson we're going to be doing is all about simplifying radicals, particularly square roots. The thing I want you to notice is that on this entire page, every single one of these is missing the index, which means that every single one of these is square roots. Next year in your Algebra 2 class, you'll get into how to better handle higher order radicals. But for now, we're just going to be doing square roots. So, just like a fraction can be simplified, so these are the directions here. We'll go over those in a second. I mean, just like a fraction can be simplified, 3/15 is going to reduce down to, we're going to find the largest common divisor that they share. Looks like 3 divides both of these. So this could be rewritten as 3 times 1 over 3 times 5. And then these two are going to cancel out, leaving me with a reduced fraction of 1/5. So just like a fraction can be simplified, a radical can be simplified as well. Now, everything that we do this unit, we're going to put it in simplified or reduced radical form. Now, in order to do that, we're going to need a list of all of our perfect squares. Now, every single one that goes down this list inside the square root is a perfect square. Now, the square root of 1 is just 1. The square root of 4 is 2. The square root of 9 is 3. And honestly, I've written these out in order so you can just number all the way down. 13, 14, 15, 16, 17, 18, 19, and 20. So square root of 324 is 18. Now, what that also means is the opposite. 20 squared is equal to 400. This number squared equals the radicand here. We're going to be needing that list in order to simplify our radicals. Okay, so I'm actually not going to specifically go over these. You can look at them later. I'm going to be incorporating these into showing the examples of how to do it. But the general idea is first we're going to take our radicand and break it down into its corresponding multiples. Now, we don't want to just find any multiples, like for example, 45. If you remember breaking these down into factor trees, it could be written as 15 times 3. However, this is not a good way for us to break it down because neither 15 nor 3 ends up on this list anywhere. We're trying to find one of these numbers that divides into it. Okay, so if I start going down my list, and just to simplify things, I want to go from the bottom up. Like I know, for example, 64 definitely can't, 49 can't, 36 doesn't, 25 doesn't. If you don't remember how to do that, or know all your multiplication tables or all your factors, all you have to do is start testing them. 45 divided by 36 is not a whole number, so it doesn't work. 45 divided by 25 is not a whole number. 45 divided by 16 is not a whole number. 45 divided by 9 is 5, which means that 45 can be rewritten as 9 times 5. So what I'm going to do on my simplification step, number 1, find this. Find the largest one of these numbers that will evenly go into this into your radicand. Then we're going to rewrite it as, now we're going to put these two numbers in here, or if you're looking at your calculator, these two numbers. I want you to always write the perfect square first. So it's 9 times 5. Notice all we've done is broken this 45 out into 9 times 5. Okay, by the way, that's step 1 and 2 from your list over there to the left. Sometimes I'll circle this just to make sure that I know which one is the perfect square. Then we're going to perform the square root. We're going to bring the 9 outside. The square root of 9 is 3. If you don't know that, it's right here. Square root of 9 equals 3. Now this 5, we can't take the square root of, so we're going to leave it alone, and our answer is 3 square roots of 5. That's our simplified radical form. Now, one of the things that I start seeing people try and do is start adding an extra square root sign. Guys, whenever you perform the square root symbol, or perform the square root operation, the symbol is consumed. Okay, just like, you don't have to write this, this is just an example. I tend to see this thing a lot. The square root of 9, and then on the paper someone will write equals the square root of 3. Well, that's just flat out not right. And here's why. If I do 9 plus 7, that equals 16. You would never write 9 plus 7 equals 16 plus. Because in the act of performing this, this thing right here gets consumed, and now the plus sign is completely gone and does not exist anymore. So please do not write that square root in front of the 3. It's going to be there, or going to be gone as soon as you take the square root. Okay, now 24. Let's do the exact same thing. Let's look for the biggest one of these numbers that evenly goes into 24. So 25 definitely not, 16 doesn't, 9 doesn't, looks like 4 does. 24 can be rewritten as 4 times 6, and notice that I'm writing the 4, the perfect square first, and circling it. Now I'm going to perform that square root. The square root of 4 is equal to 2, and then times the square root of 6. Did you need to start your test?
No, I should work on the 7-4 sign.
Okay, it should be unlocking. Go ahead and start. All right. Now over here, this one appears slightly different because we've got our 2 out in front. Now, that's going to change one thing we do at the end, but not by that much. So the first thing we need to do is find a perfect square that evenly divides 128. So let's go ahead and try and find one on this list. And again, I don't know these, so I'm just going to test them as I go. 128 divided by, let's try 64. Hey, I hit it on the first try. Divided by 64. So this is 2 times the square root of 64 times 2. Again, that perfect square went in the beginning. Now, our 64 is going to come out. Notice I'm going to write this 2 right down. I just copied it directly down. Times the square root of 4 is 8 times the square root of 2. This 2 comes down. Square root of 4, or 64 is 8. Now I'm going to perform this multiplication. 2 times 8 is 16 times the square root of 2. So the only additional step here is that you have to perform this multiplication at the end. Moving on to number 4. Again, I want to find a perfect square that evenly divides into 500. So 6 times the square root of. Now, anytime I've got double zeros on the end, it's pretty simple to find one of them because it's going to be divisible by 100. This one is 5 times 100. Oh, and see, I should have written it the other way. I'll put it on the back here just so you can see I'm still writing putting the circle around it. The 6 gets copied down. Square root of 100 comes out as a 10 times the square root of 5. So now I'm going to perform this multiplication. 6 times 10 is 60 square roots of 5. And there is my simplified answer. Now something you want to go ahead and do is go ahead and check back each of these radicands. Make sure that there's not another radican or another one of our perfect squares that will divide into it. In this case, 5 and 2 are all prime, so I know nothing will go into them. 6 is 3 times 2, which 3 and 2 are not on this list, so we're okay. All right, now let's look at multiplication of radicals. Now, anytime you're multiplying two radicals, you're going to multiply the coefficients out in front, which in this case there are no coefficients. Here you would multiply those two together, and you're going to multiply the radicands together. So in this case, my coefficients are the hidden ones. 1 times 1 is 1. And then 5 times 7 is 35. So just multiply the radicands, multiply the coefficients. It's that simple. Afterwards, we want to check to see can we divide any of our, or can we simplify this further? And in this case, 35 cannot be divisible by 36, 25, 16, 19, or 4. So this can't be simplified. It's just square root of 35. All right, on number 6, again, no coefficients to worry about. So this comes down to the square root of 16. 8 times 2 is 16. Now, since 16 is one of my perfect squares, well, the square root of 16 is just 4. Now, in this case, there's nothing left on the inside, so I don't even write the square root anymore. It's just 4. I mean, this is just a simplified version of, or a more complex version of that. Okay, notice there is no square root sign. It's just 4, which is why I just have 4 there. All right, now number 7, whenever I do have coefficients. Okay, 5 times 4 is 20, and then there's my square root sign. 2 times 3 is 6. And now let's go ahead and check to see if the 6 is divisible by anything. The only one smaller than 6 on that list is 4 and 1, and 4 does not divide by 6, so this one is just 20 root 6. All right, number 8. Again, I've got my hidden 1 right here. 3 times 1 on the outside is 3. 8 times 12, I honestly don't have that one memorized. 8 times 12 is 96. And now let's go through and see, does 96, is it divisible by one of our perfect squares over here? So 96 divided by, definitely not 64. 49, no. 96 divided by 36, no. 25, no. 16, yes, it's 16 times 6. So this is 3 times the square root of 16 times 6. I'm going to circle my perfect square. Let me get to where you can see it. And now, again, the 3 gets written down. Square root of 16 is 4. Forgot my equal marks on all these. And then times the square root of 6. And then 3 times 4 out front is 12 square root 6. All right. Now for the next section. Anytime I have a square root on bottom. Now there's a few things in math that we consider just kind of ugly or not pretty. We don't want to do them just because it's not proper, essentially. One of those things we don't want to do is have a square root in the denominator of a fraction. Okay, you'll get to another one of those next year when you start talking about complex or imaginary numbers. Another thing that we just don't allow to be in the bottom. Now, if we do have a square root in the bottom, we need to do what's called rationalize it. Now, the reason it's called rationalize is because the square root of 3 is an irrational number. Square root of 2 is an irrational number. Irrational number is sort of like pi. It's one that does not have a fraction equivalent. Pi, even though we round it here, it actually goes on forever. Never stops, never repeats. The square root of 2 is another one of those. It's one that never stops and never repeats. We just round it here to this 2. We don't like having those types of fractions down, or those types of decimals down the denominator. We want those to be up in the numerator. And there's some various reasons for that, but we're not going to get into those right now. Now, it's actually pretty simple to get them out of the denominator. Okay, we're actually going to invoke one of the most powerful tools you'll ever have in mathematics, and that is to multiply by 1. Now, that sounds kind of ridiculous. Multiply by 1 doesn't do anything. Yeah, we know that 3 times the square root of 2 times 1 is 3 times the square root of 2. We've done nothing. But what if we did this in a creative way? You know that 1 can be rewritten as a fraction of 1 over 1. It can be written as 2 over 2. It can be written as x over x. It could be written as smiley face divided by smiley face. It does not matter. As long as you have the same thing in the numerator and the denominator, it equals 1. And if I multiply by any of these, it's the same as multiplying by 1, so I don't change the fraction. Now I'm going to do that in a creative way that is going to eliminate the square root on bottom. The only way to do that is to take this radical here and put it both in the numerator and the denominator. Now, this square root of 2 divided by square root of 2 is still 1, okay, because anything divided by itself is 1. So I haven't changed anything here. Now, I'm going to just multiply these out. 3 times the square root of 2 is 3 root 2, divided by, and now we're going to multiply our radicals like we did in the section before. Square root of 4 times square root of 4 is square root of 4. I said that wrong. Square root of 2 times square root of 2 is square root of 4. Now we can simplify it and say that this is 3 square root of 2, and now the square root of 4 is 2. So there I have the exact same thing, just written different ways. And if you don't believe me, let's try it. 3 divided by the square root of 2 is 2.12. And now 3 times the square root of 2, 3 square root of 2 divided by 2 is still the exact same number. Okay, this one is just considered prettier because it does not have the square root symbol on bottom. All right, now for this one, we're still going to take our denominator, which is square root of 18, on top and on bottom. Now let's go ahead and start simplifying. 5 times 18, I don't know that one, is 90 over, square root of 90 divided by 18. Now let's see if we can simplify the square root. Let's see, 90 I know is divisible by 9, so this is a square root of 9 times 10 over 18. And now the square root of 9 is 3, so 3 square root of 10 over 18 comes out. And now I want to see, can these two reduce? Okay, so if I forgot about the 10, 3 divided by 18, well, 3 divided by 18 can reduce down to 1/6. So this is 1 square root of 10 divided by 6, because 3/18 reduces to 1/6. Now you don't have to write that 1 because we never have to write a 1 whenever it's the coefficient. All right, 2 more. I know this has been a lot. Just 2 more. Add or subtract. Now the first thing you got to know is you can only add or subtract if they have the same number under the radical. If the radicands are the same, you can add them together. Now, what I want you to think about here is that if this had been 3x plus 4x, you would just rewrite this. 3x plus 4x is 7x. This is going to have the exact same pattern here. 3 root 7 plus 4 root 7 is 7 square root 7, because 3 plus 4 is 7, and then these symbols, this symbol here does not change. This symbol here does not change. So 3 root 7 plus 4 root 7 is 7 root 7. Same way that 3x plus 4x is 7x. Okay? Now, if they don't have the same radicand, I can't do anything. But I know how to reduce radicals. So I'm going to reduce both of these. Okay? Now 125, I'm going to see 25 on the end, so I know it's going to be divisible by 25. 4 times the square root of 25 times 5, I'm going to go ahead and circle that, minus 2 times the square root of 45. We actually did this one up at number 1. You can look back at it. This one is 9 times 5, and I'm going to circle that. So 25 comes out as 4 times 5 times the square root of 5, minus 2, square root of 9 comes out as a 3 times the square root of 5. Let's go ahead and simplify these down. 4 times 5 is 20 root 5 minus 2 times 3 is 6 square root 5. And now, after I've reduced them, they do have the same radicand, so I can subtract them. Well, 20 root 5 minus 6 root 5, 20 minus 16 is 14 square roots of 5. Okay? Whew, I know that was a lot. Good news about these recordings is you can always go back and rewatch stuff if you need to. Feel free to ask me questions. You're going to have an assignment that's going to have a bunch of these on it that you're going to have to solve. And this is one where I do not simplify it down because honestly you need to just practice and practice and practice. You're going to have a lot of these. In order to accommodate that, I'm going to make the quizzes a little bit shorter than normal. So go through. Top section is just simplifying, just like we did on section 1 up here. Second section, we're going to multiply them. We're going to multiply your coefficients, multiply your radicands, and then simplify. Rationalize, all you're going to do is put the denominator on top and bottom, multiply and reduce, and then on these, simplify if needed, and then once you have the same radicand, add them together. Okay, I know it's a lot, but this is one of those assignments that's going to go pretty fast after you start getting the pattern down. And I need you to get that pattern down so you have it when we start on Pythagorean theorem stuff. So that's it for now. Good luck on your assignment.